In this video we're going to be talking about hyperbolic angles and angle measurement. So in our hyperbolic half-plane model, let's pull the edge up here where we can see it. We are looking at angles. And remember, angles are defined exactly like they are in Euclidean geometry. It's a union of two rays with a common endpoint. Of course, these are hyperbolic rays. So here we have a hyperbolic ray BA and a hyperbolic ray BC, and they have a common endpoint. So there is a hyperbolic angle. There it is as well. So how do we measure it? Well, one of the nice things about hyperbolic geometry is that it is, at least this model of hyperbolic geometry, the hyperbolic half-plane model, is that it is a conformal model. So what does it mean for it to be conformal? It means that angles are measured exactly like they are in Euclidean geometry. Well, what do I mean by that? I mean, this is not a Euclidean angle, so what do we mean by that? Well, how do we measure two curves, the angle formed by two curves in Euclidean geometry? Well, if they have a well-defined tangent line at the point where they meet each other, okay, then we can just measure the angle between those tangent lines. Of course, these are circles, so they certainly have well-defined arcs of circles in Euclidean geometry, so they have well-defined tangent lines. This line here is the tangent line to this circle at this point B in Euclidean geometry. This is the tangent line, or tangent part of a tangent line array, tangent to this circle here, going through A and B, tangent at point B. Then we're just measuring the angle between these two, this angle here, angle AE, BCE, and we're just measuring that angle, and that is the measure, the hyperbolic measure of this angle ABC. Completely different, by the way, than the measure of this Euclidean angle, going here and here. That may have a completely different measurement in Euclidean geometry. So that Euclidean angle is not what we're measuring. What we're measuring is this Euclidean angle formed by these two rays here, which are tangent to this. And so that's how we would measure that. And it's set up, I need to keep my point in the plane. And you can see as you go around here what happens to that measurement. Okay, and I have given this when Wesley did this sketch, he is thinking of it in a directional angle, so there he does have a negative sign here. For the way we're measuring it, it would be only a positive measurement. So let's see if I make sure. So now we're going, the shortest rotation is negative when we go that way. That's negative. This is positive. And of course, we could just take the absolute value of that for the measure of a physical angle in hyperbolic geometry. So that's how we would measure them. Now, yeah, let's keep going here for just a second. When we have two lines meet, they form four angles here. And we do have a dynamic angle marker tool, which we can click here and this point of intersection in here, and say here and here and here. And we have these two angles. Now we can use we do have an angle measure tool. Let's see, angle measure precise, let's use that one. So if we click on this point, this one, and this one, that's going to measure it in radians, and notice it did turn out to be exactly, well, negative power 2 radians because of the order I did it. So that's a right angle. If we do the same thing for this one here, that one also turns out to be a right angle. Now in general, when you have two lines that meet, okay, let's just make a couple of different lines here. So let's make a we can use, we'll just use an H line here. So here we have a line, and then let's do another line here. It met at that point there, W83, whatever. Okay, and so we can measure some angles here. Let's mark the. Let's use our angle marker tool, and we'll mark here this angle and this one. This is a pair of what are called vertical angles formed when we have a line here. Let's see. Let's go over here. I can see all my points. Let me just take these two. Let me make them a different color. Now let's make them black. Okay. Now, if I measure that angle with my angle measurement tool and click here, 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 that gives me a measure. Keep selecting the negative direction. Okay. And then actually, let me do it so that it's in the positive direction. So here, 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 Alt, and then select the H distance, H measure of the angle precisely. So that's the other way we can use the tool. And then let's use the same tool and do this one. If we want to go positive direction, should be this one, this one, this one, I believe. Okay, what you notice here as we manipulate that, let's see, these 3 points here are the control points. So as I move this, I need to make sure this is on the other side there to get my marker right. But if I do that, if I get it on the other side like that, then we notice that these have the same measure. And of course the proof is exactly the same in Euclidean and hyperbolic geometry. So vertical angles have the same measure, pair of vertical angles. But not necessarily the same as the measure of the other angle. So that angle there, of course, is maybe a bit different. Okay, but of course one thing we notice is if we calculate their sum, that plus that you get exactly pi radians, the measure of a straight angle. Just like you do in Euclidean geometry. To get this thing, I need to make sure these points are on the other side. There's some ways I can probably force that, but I'm not going to take the time to do that right now. So we get that. But if you ever get a spot, there's a spot somewhere in here. I'm really close now. That looks about as close as I'm going to get. There's some spot where they all four are the same. And when that happens, we call that angle a right angle. And of course, it's going to have measured pi over 2 radians. And so then we say the two lines are perpendicular. So let me do a hot show here. Oops. Okay, and these will be so that's to show a pair of vertical angles. Okay. And if you get not only the vertical angles congruent, but all four angles formed here, all four proper angles, then we say that these are perpendicular, and the type of angle formed then is what we call a right angle, and it'll have measure pi over 2 in radians. Now, it turns out, this is two different theorems. It turns out that given a line, like line AB, and a point not on a line, C, okay, then there exists exactly one perpendicular through point C perpendicular to the line. AB. Let me just name that X for where it crosses. And maybe we'll call it D and E. Okay. Now, on the other hand, if you've got a line DE and a point F on the line, there exists exactly one line through that point perpendicular to the given line. Those are two different theorems. The proofs are different. They require a little bit different things to prove that. We'll prove those formally, probably as tasks or as someone's presentation in class. Okay? But we can do this. Now this is going to let's hide that. And let me make a hide show for that. So remember what that is. Okay, and we go through here and find some different constructions. Also, a related thing is that every line segment has exactly one midpoint, and that is done here. Let's get rid of that. So M is the midpoint here. Okay, and so there are the two types of things there. Okay. Now we have custom tools. Talks about using them here, so I'll just use them. The first one is let's see, perpendicular line, a point on the line. So we first define okay. So the 2 points selected are on a line. So let's do this. Let's first make a line. Okay, and then we select this by selecting, let's see, perpendicular on the line. I think we select a point. Yeah, we select a point, and then the second point we pick basically needs to be on the line. And so those 2 points define the line, and they also, the second one is the point that it goes through. So if you're doing this on an existing line now, the two red lines now are perpendicular, and then these 2 points here control the line. If you just do this out in a free setting here, then you select your 2 points. You've got the perpendicular line here, but what you're not seeing is the other line. So you need to maybe use a line tool and do this. What this does, of course, however, if you move this point, it's adjusting both the perpendicular line and the original line. Okay, but like I just said, if you already have an existing line and you want to make a perpendicular to a point through it, then you select any point on the line, like just one of the control points is fine, and then select another point. What's happening there? Okay. It works. That's strange. Let me try that again. So select a line. Okay, and on the line, do I need to select 3 points? 1. Actually, I can select any 2 points on the line, and then this point then becomes free. If I want it to be a specific point that's already on the line, like say this one, then I hopefully can do this. Select these two, and oh no, it's not going to let me do that. Unfortunately, it's not going to let me merge those points. Okay. So anyway, I can make it like that. Now the other tool is, let's say, given a line again. Okay. Then we can pick a point and a point not on the line, and we want to make a perpendicular to this line through that point. So I should be able to go ahead and just select all. Let's see if I can do this, and then Alt. Okay, I've got too much selected. Okay, I think I just need the 2 points and this point. Let's see, Alt, perpendicular not on the line, and there we go, like that. Or I can just do it this way, select that, and select 2 points on the line, say the control points, and then a point not on the line, any point I want. And now, as this moves around, it's perpendicular to there. So it's a unique perpendicular. Okay, and that basically works the same way as the Euclidean tools. If you're given a Euclidean line, okay, and then you can select a point not on the line and the line itself and say construct a perpendicular line, which it will do. Or you can select a point on the line, say any point on the line, and the line itself like that, and say construct a perpendicular. That's unique. Both constructions are different types of constructions. It's actually done a different way with the compass and straight edge, but it is something that is unique. So it is, we can do it that way. Okay. Finally, I want to do one more thing about angles. Well, two more things. There's a unique angle bisector such that these two angles CBD and DBA are congruent. Of course, D is between there. Okay, and there's a way to do that, of course, is define, let's make an angle by making a ray and then another ray with a common endpoint. And the tool works like this to make an angle bisector. There's a tool for that too. H angle bisector. You just click on a point, the midpoint, and then the vertex, I should have said, for the middle one, and then the other one here. And now this new object here, then you can color it whatever you want. You know, the blue now is the unique angle bisector. Okay, so we have an angle bisector tool. Okay, finally, one other thing. Let's talk about a Euclidean construction. If I want to make a Euclidean angle, I can do this, of course, and I can fix it. But what if I want to make a specific, and I can measure it, but what if I want to make a specific size angle? Then here's how you want to do it in Euclidean. So you can say make it based on a parameter or just give it a specific thing. So let's do a parameter, and we want to make an angle parameter. You name it whatever you want, angle. Okay, and give it an angle measure in radians, like well, 1 radian. Why not? Okay, so there's 1 radian. And what we want to do is then we want to rotate this either the positive or negative direction 1 radian. Right now we're going to do positive direction. So what you do is you select a point that's going to be the center, and we want to say transform mark center. Now we select the ray that we want to rotate, and we say transform rotate. Now at this point I can put in a specific angle and it will be that, or I can click on that angle and it'll say let's use that marked angle, or I can mark the angle before I do this. And now I'll rotate. So now there's an angle of 1 radian, no matter where I put it. Okay, so we want to be able to do the same thing in hyperbolic geometry. And so basically we can do the same thing. We can denote a hyperbolic radiant thing here. We can make us a ray. Now we're going to need to be a hyperbolic ray this time. So an H ray. So there's a ray. I can take and mark the center. And then I want to rotate this in the hyperbolic way. So I can, let's see here, H rotation here, and I think I have to mark, I think I click on the center, let's see, a radius. Okay, you do it, it just rotates one point. So let me remember how this tool works. Okay, it assumes that we have a coordinate system and a hyperbolic plane. We need a point, an angle, and a point. And the first point is, I think, going to be the center. Okay, so let's try this. So point, angle, point. So for H rotation, I think we would click center, an angle, and then a point. And that rotates that 1 radian. And now I can go ahead now and go back to my angle tool, or my ray tool, and finish out the ray. So it rotated this 1 point that much, leaving the hyperbolic distance the same. So if I do my H circle by center and point, and go to here, this other point, no, it's not staying on there. Maybe I didn't. Maybe it didn't do exactly what I thought it was going to do there. Okay. I think it's still correct. Let's do our H angle measurement and measure that angle. Oh, something's off a bit. Uh-oh. So I need some work on this tool. I need to figure out what's up with this. So I need to do a correction on this tool. But anyway, I'll see if I can hash through this and figure out what's happening with the tool and get this worked out, because it should still be the same as this right here. Okay. So anyway, if we get the tool working correctly, then you'll be able to do the same thing that you can do with Euclidean geometry with that tool as well. So I'll come back to that whenever I can get it fixed. Alright, that's a good introduction to hyperbolic angles, perpendicular lines, rotation, several different things, angle bisector, several different topics from hyperbolic angles.